our new campus rep, saying, I expect to hear something next week or last Friday. So we had a conversation, some of us at PERC, talking about whether or not we should just I can get an AMD CPU GPU stack that because Patrick Chow, who's committed to giving us the server with the AMD Epics, he said I can do Instinct. That's in my wheelhouse. I run that product line. He can't do the GPUs, and he said you're on your own to find GPUs. So I've been trying with NVIDIA, and I feel like we're getting really close because last time it took us until about now, and we didn't get a system until the end of September, like September 29th.
Yeah.
And so I was hoping he could come through, but how do people feel about we bail on NVIDIA? I'll just let them know, look, if you can't commit now, then we have to start trying to get something, and I'll reach out to Patrick. So what do you guys think?
Yeah, it's very unfortunate that there's no commitment.
I think there's a commitment by him, but he's new. He just took over last year from Dan Dowling, who we had some great events with him.
Mhm.
Remember the one at their annual meeting where somebody got a card at the end of the there was a drawing or something. So Dan Dowling was trying to formulate relationships. So he's new. He just might not have the connections. So I just don't know when to make a cutoff date for that.
I can't really comment on cutoff dates because I don't have experience on how long these things take. Marine, that's
Yeah, it's a delicate dance.
yeah.
I feel like the cutoff date is pretty soon because even if they say, yeah, we can do it, and the lead time is 6 weeks, right? Or something like that, which doesn't seem that unreasonable. Then we're going to end up at the end of September again.
You know what I might do, Brian, and I'll CC you and Andy and Marty maybe. I'm going to reach out to Patrick and say, hey, NVIDIA wants to, but we're just not getting any confirmation. And I'll ask him how long would it take for him to give us a AMD server, and then if we add an Instinct, how long would that take?
Mhm.
So I think it's time for me to reach out to him.
I have a question. Is it possible, like, if there was a long lead time, that we could like borrow one from SDSC and replace it when the loader comes in?
Borrow an NVIDIA GPU card?
Yeah.
Well, we still have the server from SCC23 sitting in a room boxed up. I
Yeah.
might ask him if we could just pull that out and start working with it.
Well, that's true too. Yeah, I mean, until the new
They
one
can't
comes.
get me a shipping label. This is just
Yeah.
ridiculous. So we actually have hardware we could start working with now. Neil.
That's not a bad, since we're using the same vendor, maybe they'd be willing to do that for us. Like, I mean, they can't give us shipping anyway, so it's like, we'll ship it back when we get the new one.
Yeah, and so
Right.
Kai and who else was there last year? The server that we've got, I think does it meet the requirements for we need 3 servers.
It pulls more than 2000 watts. So we need to pull that down, and then we need 2 other nodes that I guess we can fit under the power budget. That's about it.
Okay, and we've got the 2 single CPU nodes that at least we could be doing 3 node AMD hardware while we wait for Patrick to deliver what we really need.
Yeah, I mean, a lot of the porting, making sure it runs on the hardware can be done with a single node. I think there would be a lot of advantage.
I mean, the only difference is that we have the two CPU nodes we have don't have accelerators. So,
well, right. That's what I was meaning, is we could at least be working with 3 CPUs, because one problem we had last year was installing the right operating system and the right software for a 3 node cluster.
Right.
The one
We
thing
failed
that-
at that. Wait, I won't say fail. I'll say we didn't succeed as well as we could.
Yeah.
And so there's just still some work there, but at least people can start working on some hardware.
Yeah, I think that's a good idea, even if some stuff is missing and you might not be able to set up, like, there's no InfiniBand cards and
Mhm.
or the classes should have InfiniBand cards or some equivalents on whatever Mellanox or I don't know
Yeah.
what we'll get. And of course, also with the GPUs, I think, if you get a box from AMD with AMD GPUs, they're probably going to be the same because the MI300s are not out yet. I don't think so, right? And so those, do you remember what that was, Kai? What did you have? MI250?
MI 250.
Yeah, so there's
And
nothing better yet.
I don't think MI 300's out yet. Yeah. Yeah, announced in May. So
All right, I will make a note and I'll reach out to Patrick. And what we need to do is set up a meeting with him to discuss. And I'll ask him if we can use the hardware that's still sitting in a box. It wasn't that hard to pack it back up. And I don't even know where it is right now, but it actually became a point of contention with the operations people because for months it just sat in a hallway.
Sitting there.
So,
Yeah.
all right, so I'll work on that and get that rolling and CC the mentors, the key mentors who would be part of that conversation. And at the same time, what we need to do is have an idea of what current server do we want. Did we nail all that down, Kai and Brian, when we were first reaching out and making our architecture plans?
I think it was like it was like analogous to having 4 GPUs per node and having them all them all be the same node, like the same type of CPU node.
Did we choose a CPU though? Like if we had
I
to say
don't
Supermicro?
think so. We had one like, I mean, best case we used the same or better CPU that we had last year.
I mean,
And
we
then-
went to Intel and then they said, oh, we can get you AMD, right? And then
Yeah.
And
But
what
I think
server that would hold CPU and 4 GPUs idles at like enough that we could have all 3 idling at the same time and not consume too much power? Did we talk about that? I don't remember.
Not specifically, I don't think.
Okay, so I think this coming Tuesday, we should talk about the hardware in
Mhm.
addition to some training topic.
Yeah, I think I could, people on the team want to start looking at some of the Supermicro
Yeah.
SKUs and just say, because at the end of the day, we want to say, this is the SKU we want. So they have a very specific idea. Otherwise, we'll go back and forth with them.
And I do need to reach out. I think we originally asked NVIDIA for 8 GPUs per node. Are you saying we only want 4?
Well, that's
My original
was it 8?
draft of an architecture showed 8. Can we even support 8?
My assumption for the 4 is it's enough to where it fits under the power budget because most of the GPUs are around 400 watts.
Because that's a big difference in the ask of 12 GPUs and 24. So 3 times 8, right? And so I'll get back to NVIDIA, Andrew, and make sure he's got that number. I don't remember what I asked him for originally, but my cartoon drawing had 8 per node. And that we never changed that. So if 4 is all we're planning on, then that's all I'll ask for.
Okay. Yeah, I'll look through our emails to see.
Why don't you, think about that. Maybe we can meet about it or talk about it at the end of the meeting today.
Mhm.
All right, that's all the preliminary stuff on my notes. So with that, Brian, you want to talk about bare metal clustering?
Sure. Before I do that, one other thing that we might want to consider if we can't get NVIDIA GPUs is to ask the committee about it. Because if we can't get them, it's likely other teams can't get them. And if one of their benchmarks doesn't run on AMD, that's a problem for all those teams.
We're going to have
Not just
that again.
us.
That's right. ML doesn't run on Instinct
So,
that
and
we
if
know
we're
of,
not
right?
the only team who can't get NVIDIA GPUs, it's going to be a disadvantage for everybody. So they may want to consider like, hey, it's a CPU only benchmark or something like that. And otherwise,
Sorry, what part of MLPerf doesn't run AMD?
it's not been ported. I mean, it might run, but if you go look at MLPerf results, there are no results for AMD.
But most of it's just TensorFlow and PyTorch, right?
I'm
I
sorry.
believe so.
I think most of it's PyTorch or TensorFlow, right? Which should run.
It may run, but I actually I don't know. I mean, if you look at all the published results for MLPerf, there are no AMD results. And there's a bunch of Reddits which say, oh, it's not optimal. And there's actually a GitHub we looked at last week where
Okay.
people are trying to tune it. So I think it's a known problem with the benchmark, at least in terms of what we were able to find out.
Well, for the MLPerf, I noticed that it mentions that software are based on TensorRT and CUDA, so I assume they're only based on the NVIDIA GPUs.
Well, those are libraries that help optimize inference workloads for sure on NVIDIA GPUs. So yeah, I'm sure AMD probably doesn't have something equivalent yet, but anyway, I mean, we could look at it.
We could send a note to Derek Wyas, who was a mentor last year and worked hard with Anish to try to port and get the reproducibility, Python-based reproducibility application running. And Derek just gave up and told Anish, just go do it on the cloud. So he was very helpful. So we could send him a note and ask him as well.
Yeah, it's not really to have accurate information before we ask the committee, but that was what we were able to determine.
Yeah, I mean, one thing I would definitely ask the committee about the MLPerf is, do they really want us to be prepared to run every single benchmark? I mean, that's a lot of combinations of things. Like, it's more than every other application that we have.
I think
it's a very specific subset of the benchmark.
I think it'll be a subset.
Okay.
It's just inference.
Yeah, but there's probably 20 combinations just on the inference data center version. Right, there's offline and server. I mean, they have different like constraints.
I did not realize.
Yeah. And categories of like types of tasks, right? You have like image classification, object detection, like natural language processing. There's like question answering. Like there's a range of different tasks, and I'm just curious if they actually want us to be prepared to do all of them.
If you phrase me a question, Marty, I can, and we can send it directly to Jeanette Tillotson, the chair. She's really flexible and really adaptive and nice and doesn't mind questions. So
okay.
I would, yeah, I'll put her email in there, and if you just want to send me a question, I don't care. But let's ask her directly and tell her we're having trouble getting our GPUs. So how much MLPerf are they expecting people to run? They usually do subsets of things anyway, unless they expect you could run all of the tests in 2 days, 48 hours. You can be sure they'll have us run enough that it would be 48 hours. Just under, so you have just enough time to finish and turn in a report. For reproducibility, I don't know about MLPerf. They'll probably just have you turn in a bunch of numbers and results. But for each of the applications, they give you a format and what they expect to see. Okay.
So yeah, this wasn't included last year. I feel like I remember they gave like just a standard, hey, run the script and give us the numbers basically.
Yeah, last year they had IO 500. They had listed MLPerf but dropped it. It was temporarily in the pool and then they dropped it.
I see.
Yeah. And I was talking with Jeanette, and it turns out every year is different and it's at the will of the committee chair. And they do, it changes every year, and they think that's a good thing. And it probably is. It keeps keeps things fresh. So a question like this, we can ask her about ML if they've made up their mind about how much needs to be done.
Yep. Okay. So should I get started on the hardware?
Sure.
Okay. So I made a couple of slides. They're very rough, just to kind of keep me reminding what I'm trying to get across. So I apologize. The slides are kind of crude. I put them in the team folder. And I'm also going to use some slides from my other class, which might be helpful. So first of all, I want to talk about just in general what the kind of hardware we're running on and why. So if you just think about high performance computing, there's really kind of two things that people want to do. One is they want to compute something faster. Faster might mean I can compute something, where the result is useful to me. Like if you're doing predictions of weather, for example, you want to predict the weather before it happens, or you might want to do something more accurately, or you might want to try to solve a problem that isn't solvable on a smaller machine for capacity reasons, let's say. And there's really two ways that people think about making things go faster. One is to just have more capable processors. Think back 50 years ago, 40 years ago, we ran at a megahertz, and now we're running at cycle time of over gigahertz, a couple gigahertz. And so I can just speed up the processor. I can also do things in batches, like, going back even to like the 1970s or earlier, people thought about machines that process vectors. And so I can design things that operate on a smaller time scale at higher frequency. And then, of course, when you run into barriers where you just can't clock any faster, or you can't go any faster on a scalar performance, you think about breaking the problem down into divide and conquer. Let's run it on multiple processors and process them in parallel. And that's pretty much the regime we're in now when we talk about supercomputers, almost all parallel computers. And the kind of computer we're going to build is a parallel computer. So the next question is, well, what kinds of computers are parallel computers? I think that's the next question. Oh, okay. Parallel computation, C267. Okay. So what is parallel processing? Well, I want to go faster. I want to do it more efficiently. And basically, I'm decomposing my workload onto simultaneously executing physical processing units. Okay. So like if I have a problem that takes time n on one processor and I want to run 100 processors, I'd like to be able to ideally compute that in 1/100th the time, or 100 times faster. Okay, and that's called the scalability of the problem. Now, the parallel resource doesn't really happen for free. There's always going to be some overhead when I divide the problem amongst multiple processing units. There's going to be some amount of communication that has to happen between those processing units. And there's a number of ways that can happen, but that's always going to be additional overhead that my original single-threaded one processor didn't have to do. So there's some cost to going parallel. Let me see what the next slide is. I remember. And this, I just talk about different kinds of parallel processing here. Okay, so this is kind of illustrating the fact that single scalar performance has increased in performance rate. This is a log scale, so this is actually exponential when you see a straight line. But then, in the last 20 years, 10 years, more like 20 years, things have slowed down. We can't go faster just by brute force, making the processor go faster. So, and the reasons for that have to do with power, basically. I'm getting a lot more transistors, but I can't remove the energy that's dissipated in those transistors efficiently, right? As I go faster, I dissipate more power. At some point, I'm dissipating so much power, I can't actually dissipate it. The heat the energy density on the silicon gets to be too high to be sustainable. And so that's kind of this power wall you might hear about, this power wall here, which illustrates the fact that even way before the turn of the century, we looked like the clock rates were getting faster, but the power was actually increasing with that clock rate. And so it got to the point where it's not sustainable. Zishan, you have a question?
Yeah, so I have a question about if the room temperature superconducting comes true, the LK99 material, how much performance boost will this happen to everything computing?
I have no idea. That's not something I'm familiar with. There's certainly a lot of technologies that have been purported in the past to like this particular physical process or semiconductor technology is going to revolutionize, computing. That in my career, that has rarely happened. We've rarely seen these kinds of inflection points. So I don't know, to be honest about it. In my career, CMOS has had amazing staying power, right? It's like once it kind of became the prevalent technology, it has been the prevalent technology for all my entire career. When I started my career, there was a good amount of bipolar implementations, different technologies, germanium instead of silicon, but we've been with standard CMOS, with variations, 3D transistors, all that kind of stuff, but basically same technology. So I don't know. That's a good question.
I see. Interesting.
It won't happen this year. So these are the kinds of things we're facing, this power wall, and that's why parallelism is kind of inevitable. So let me go back to the other slide. Oh, this is a cool slide. Let me just show this. This is one that I think Pat Gelsinger, when he was the CEO of Intel, came up with way back, probably around 2000. And it shows kind of the heat density. So if you look at kind of the trajectory we're on by increasing the clock frequency of CPUs, we had the heat density of like a hot plate here, and then kind of the heat density equivalent to like a nuclear reaction, and then the heat density of like a rocket nozzle, and like the heat density of like the sun's surface. So we could tell, even back in 2000 or late 90s, we could tell that we were on this course where the path we were on was not sustainable. And that's even accounting for the fact that we were going to get down to geometries like today, like 3 nanometer, which was unheard of back then. It's hard to imagine we could get geometries that small. But, we kind of knew that couldn't just keep going the same way we were going. So that meant parallelism was inevitable. Okay. So when we parallelize a problem, there's really two things that we think about from, this is kind of a CSC23 point of view, or HPC point of view, which is that there's a problem we want to solve. And oftentimes, I should say oftentimes, a lot of the times, if you're lucky, the problem you're trying to solve is actually fairly simple. It's just massive. For example, if I want to multiply some matrices, I know what it takes to do the inner kernel of a matrix multiplication. It's approximately n cube computations, and they're all multiply adds, okay, where n is the dimension of the matrix. So I can characterize, well, that's the amount of work I need to do. I need to compute n cube multiply adds, right, where n is the size, one size of the matrix if its matrix is square. And there's lots of problems like that. Okay, now, ideal world, all I'm going to do is this n cube computations, and I take the n cube computations, I divide them amongst the number of processors I have. So I have 10 processors. Each processor does 1/10 of the computation, and I go 10 times faster, right? Now, in order for that to happen, though, I have to distribute that problem amongst the 10 processors. And they probably have to interact in some way. In a lot of problems, one processor computes, let's say, part of say I'm doing matrix multiply again, and I divide, remember in matrix multiply, I'm doing multiplying a row times a column, and maybe I have to divide that row into chunks and divide the column into chunks, and then those chunks have to be accumulated. So there's some communication that has to happen between the processors that are doing the different chunks of those vectors. And that's the overhead. So in any kind of computation problem that I do in a parallel machine, there's always going to be some overhead. And that's the cost of parallelizing the problem, right? And typically in high performance computing, we measure this ratio, which is the number of computations I do versus the amount of communication I do. Okay, I want this number called computational intensity to be as big as possible, which means I'm doing more compute for every message that I have to send. Because the communication overhead is just overhead. It doesn't actually add to solving the problem. It's kind of a necessary evil, right? So in all these kinds of problems, we're always thinking about, how do I minimize the cost of communication? And that's either by communicating less often, or communicating faster, or copying things so I can reduce, which is basically the same thing as reducing the amount of communication. Okay, and how we do that communication happens in lots of different ways. Let me pause for a second, going kind of fast. Any questions so far? This is kind of just the theory. Good? Okay. All right. So what are the two types of parallelism that we generally think about? There's two paradigms for, there's really, yeah, okay, I'll say there's two. There's machines where all the memory is shared. So you imagine you have a program, again, let's say we're doing matrix multiply, and the matrices are all stored in memory, and all the processors can access that memory, and all the processors can update that memory. Okay, and from a programming standpoint, it's kind of invisible, right? It's like, here's some variable in memory. My thread here can access that memory, and my thread on this processor can access the same memory. We both have the same name for that memory. That is the same address for that data that's stored in memory. And I can communicate just by storing to the memory. I update this memory value, everyone else in the system can see that. That's called shared memory. Nowadays, that is kind of a difficult thing to scale. When I'm talking about thousands and thousands of processors, it's very difficult to have them share the same memory. And there's a number of reasons for that, which we don't have to go into here. But basically, from a hardware standpoint, it becomes extremely expensive in terms of the amount of hardware I need, the ability to make the hardware reliable, the amount of power it needs to consume, the amount of bandwidth, etc. All these things are difficult to scale to thousands and thousands of processors. So that kind of motivated the other kind of parallelism which we deal with. It's called message passing or non-shared memory systems. And these systems, processor here and the processor here might be working on the same problem. And if they need to communicate, they copy data from one machine to the other, like sending an email, right? High-speed email, right? Between the processors. And those emails, those messages have to be managed by the software. It's not the way it is in shared memory where everything kind of just works, right? And finally, the other kind of parallelism we're going to be dealing with in this project is heterogeneous computing. And this is where things like GPUs come in. Those are accelerators that are tightly coupled or loosely coupled with the processor. So sometimes they share memory with the processor, and sometimes they don't. So they exhibit both shared memory and message passing semantics, depending on the particular GPU system architecture and the kind of programming languages used with them. Okay. All right, everyone good so far? Okay, so I'm going to go back to my SCC23 slides. So let's talk about memory. So, okay. So one of the problems, if you look at historically what's happened with processing and memory speed, and this is a well-known problem. If you look at what's called the CAGR, which is the compound annual growth rate. So compound annual growth rate for computation is kind of that, the red line, right? That is how much faster processors have gotten. And again, this is a log plot. So we say 60% per year. That looks linear, but it's not really linear. It's growing at 1.6 times per year, right? So it's exponential. If you look at the speed at which memory is increasing, that is, or sorry, speed of memory is how fast you can access the memory. So that's the reciprocal of the latency, right? So if I want the memory to go twice as fast, I want the latency to halve. Right? Latency is how long it takes to read or write memory, nominally read. If I look at the growth rate of latency or the reduction in latency, it's only at 7% per year. So as time has gone on, the gap has gotten bigger and bigger between main memory speed and CPU speed. If you look back to the Stone Age of computing, go back to like 1960s, 1950s, those machines, the CPUs and memories were fairly similar in speed. So if I do a load from memory on the machine back in 1950, maybe it took 3 cycles or 4 cycles to access main memory, and everything was great. Now, as the clock rates have gone up, I even look at a machine from 20 years ago running at 1 gigahertz. Well, that machine can process an instruction in 1 nanosecond, and the memory takes 100 nanoseconds. So there is a factor of 100 difference between the speed of memory and the speed of the processor. Obviously, that's not a very good way to, not a very good situation to be in. So that led to the advent of caches. So the memory hierarchy that we have in a modern machine is built of small memories that are fast and larger memories that are slow. So you've probably seen pictures like this before. It's like a pyramid, inverted pyramid. It's a pyramid, not inverted. At the bottom, we have the largest storage we can have in a machine. Let's say it was disk. Nowadays, probably solid state disk. And that's going to be hundreds to thousands to 1 million times slower than the fastest memory in the machine, which are the registers. The registers I might be able to access in 1 cycle, and the SSD or phase change memory or disk, whatever it is going to be on the order of like tens of thousands to 1 million times slower. And the trade-off I'm making is in the register file, maybe I only have like, I don't know, 32 registers, 64 registers. Not a lot of memory, maybe 1 kilobyte of memory. On the bottom, I've got terabytes or petabytes of memory. And so there's this relationship, inverse relationship between speed and size. As the memories get bigger, the speed gets slower. Okay. And so I build this hierarchy in my machine of registers, and then maybe an L1 cache, which is a little bigger, about 4 cycles away. Then maybe L2 cache, which is maybe, I don't know, half a megabyte, 20 cycles away. And then a last level cache, it's like 50 cycles away. Maybe it's up to 16 meg or 32 megabytes. And then I go to DRAM, which is like 100 cycles away, and maybe I get a couple gigabytes or half a terabyte of DRAM on really big machines, and then so forth. So there's this memory hierarchy that we deal with in machines, almost all computers we deal with now. And the reason that came about is because of the gap between memory access speed and processing speed. Okay, and that gap actually exists also in communication speed. I have a slide somewhere, I didn't bring it up. But the same slide that I showed you of the gap between memory performance, this gap here also exists between communication latency when sending a message across a network and CPU speed. Communication latency has not improved at the same rate as computation rate has improved. Okay, so we have to deal with this gap. Skip this slide. Okay, so we have this notion of caches. I'm not going to go through all that. A cache, let me just show them this slide. So a cache is just a high-speed memory. Okay, and again, as the caches get bigger, they get slower until eventually you're talking about main memory. I could modify this picture today. There's kind of an intermediary memory here. So some of the CPUs we have now have kind of a hybrid main memory. The main memory used to be off chip, now it's on chip, or it's in the same package implemented on a piece of silicon that's actually a separate piece of silicon, but it's in the same semiconductor package. So it looks like one chip. So that's high bandwidth memory. Like if you look at some of the latest Apple MacBooks, right? They have the M1 and M2 processors. Their main memory is actually inside the same chip. So there's probably another box I could draw here after L3 shared memory, which is like HBM memory, which is going to be lower latency, higher bandwidth than conventional DRAM, but still going to be quite a few cycles away, maybe 50 to 100 cycles instead of 100 to 200, or roughly speaking. Okay, so we build this memory hierarchy out of caches in our chips. And so the chip we're considering using the AMD chip, has 3 levels of cache hierarchy. And there's a trade-off. Okay, so what does a typical system look like? So our typical system here, I drew a 3-server system, which is just like the system that we're going to be using. And it's got a couple of things to note. First of all, there's usually a CPU chip, or in the case of AMD, it's actually a package with a bunch of chips inside of it, multiple chips. But it looks to us, if you look at the PC board, there's one chip there, one package. Inside of that are a bunch of little CPU cores that are all hooked up to a DRAM. Okay, this is like a CPU DRAM complex. And then there's, on the same server board, there's another CPU, which is just a duplicate of the same thing. And it has DRAM and a bunch of CPU cores. And these are connected by some high-speed network, proprietary high-speed network, which allows any CPU to see any of the memory on the server. So this entire 2-socket system here is a shared memory system. All the memory that's implemented by these DRAM are accessible by any CPU on the system, just by loading an address or storing to an address. Here you can see I have this little pink block here, and maybe that pink block gets copied into a cache here and gets copied into a different cache here. Okay, so we have a shared memory system here between the 2 CPUs that are in this one server. That's CPUs. 2 CPU chips within this one server, all the cores. So this is like, I don't know, 64 cores. So maybe all these 128 cores can access the same memory. Okay.
What does the orange block represent?
The orange block represents like a CPU DRAM complex. So typically, like the kinds of servers we will get are 2-socket servers. And so each of these is a socket with its associated DRAM. I don't know why I drew an orange block. Like in some systems, like the Intel system we wanted to get, this DRAM would be all inside the same package. So the orange block would represent a CPU package, it's HBM memory. But I think in the AMD system we have now, the one we borrowed last year, those are actually DIMMs that are sitting out on the motherboard. So the orange really doesn't represent too much of significance. But the important thing is that this entire server, any of the memory can be accessed by any CPU core. Okay. So I think I had another slide on that. Okay. Some other things to note on the system. So now this server, and now you have to think in terms of physically what this looks like. We're going to have a rack, right? It's called a 19U. Is it 19U rack? I can't remember. I think we're supposed to have a half-size rack this year. I don't remember. There was like some spec on that. Anyway, we have this rack. It's 19 inches wide. That's the number. And these CPUs, these servers slide into the rack. So there's 3 of them. I drew them side by side here, but really they're going to be stacked one on top of another. And each of those servers has 2 CPUs with a bunch of cores in them, a bunch of DRAM, and then at least one network interface card called a NIC. The NIC is what connects these servers together. Okay, so we're going to connect them with something called InfiniBand, which is a high-speed network. There's a network interface card in each of the servers, which is the way that these servers can talk to one another. And the way they talk to one another is over a protocol called InfiniBand, which, from a software point of view, we're going to use a messaging library called MPI, which is a message passing interface that that Mary's going to talk about. But basically, these NICs are the way that it's like an Ethernet card, right? We talk to servers between one another and they can send messages to one another. A CPU cannot, like here, this CPU could load memory and bring it right into its cache. This CPU cannot load memory from another server. All we can do is ask the server, hey, can I have a copy of that memory? And the NIC card will transfer a copy to my local DRAM, and now I have my own local copy of that. So all the exchanges that happen, at least in the kinds of high performance computing we're going to be doing, are very explicit. The programmer says, I want to copy this piece of data from one server to another. He makes an MPI call, and that MPI call manages to copy that data from one server to the other. If I modify my local copy of the data, none of the other copies get updated. They have to be explicitly updated by the programmer through MPI. Okay, questions about this? And the last thing I drew on these pictures are GPUs. So these GPUs are sitting in these servers, and they have access to this DRAM in a multitude of ways. Depending on the particular model, they're either shared memory or they're message passing. It depends on how we've configured what the hardware supports and also how we configure or use them with the tools that we use to write the GPU programs. The GPUs really are graphics processing units. They're really just being used as accelerators. So that you can replace that with FPGA, you can replace that with TensorFlow units, TPUs, tensor processing units, whatever different kinds of accelerators you might have. These are all, I didn't draw it here, but these are all sitting on a bus called PCI Express, which is kind of an industry standard for hooking up peripherals to the system. Okay. And I didn't draw, there's a bunch of other details like PCI Express switches and things like that that allow any CPU to talk to any PCI device. But for the purpose of this discussion, that's more detail than we need. Okay, these NICs are all connected by a switch. And this year, the competition kind of mandated that we have a switch. They gave us a power budget for it, so we might as well use it. So we'll have our system will look very much like this, maybe with 4 GPUs per server, but a NIC connected to a switch, and all the CPUs, all the servers can talk to one another over the InfiniBand switch. Okay, ooh, take a breath. Questions?
So each square represents a core, but what does that pink one represent?
The pink is just representing a memory location. So any memory location can be cached in my local cache, which is a copy of that pink memory location in DRAM. And that kind of leads me to my next point is caches are copies of memory locations. So that means if one CPU modifies a memory location, let's say I go here and this CPU changes this pink thing to, I don't know, green, then that green value should be propagated to this CPU. So it, right, because eventually this memory location is going to turn green, that is, that changes value. And so all the pink copies need to turn green. And that is called cache coherence. And that's supported by the hardware. And that's actually what makes shared memory so expensive to implement, is as I increase the number of caches and copies in hardware of a memory location, whenever those memory locations get updated, I have to update all of them, right? Or make those visible to everyone in the system. And that's done in hardware. It's called cache coherence, and that's expensive to implement. And that's why when we went from out of the single server to multiple servers and throughout the data center, say I have 1,000 different servers, it's really difficult to maintain cache coherence across the entire data center. And so that's why we have this hybrid model, which is shared memory on one server, but not shared memory between servers. Just an example, when you're running your benchmarks and seeing in the competition, if you see something called OpenMP, OpenMP is a software library that relies on shared memory. So OpenMP programs can only run on a shared memory environment. So I can run an OpenMP program on one server, but I can't run it across multiple servers. Okay, so in order to get even more parallelism, back when servers only had, let's say the server chip I had maybe had 4 cores in it. So if I had a 2-core system, I could have 8 cores in one server, but I wanted my problem to scale to, 1,000 cores. I didn't have shared memory past those 8 cores. So I had to use a different method, which is let's put all these servers together in a data center and connect them by a network, high-speed network. That's called distributed memory. So servers are connected over a network. The data are copied over the network as messages, like sending an email, right? MPI is really just like sending an email. I package up, hey, I have this piece of data. I want to send it to somebody else. I provide a pointer in memory to that location. I provide a destination address, that is, which server do I want to send it to? What process on that server do I want to send it to? And then I say send, and then the library takes care of talking to the NIC, sending it over, copying the data to the other server. So this is pretty different from shared memory in that these different instances are copies of data, and they're not kept coherent by hardware. If I change my local copy of that variable from pink to green, then all the other copies are going to stay pink until I update them, right? I explicitly have to say, oh, I updated that value. The value is now green. Okay. And the library we use for this is called MPI, or Message Passing Interface. And it's just a common library that a lot of the HPC programs are written for that takes care of this message passing between systems. I think that might be my last slide. So from a hardware perspective, that's kind of the realm they're dealing with. We're dealing with shared memory on a server and message passing between systems, right? And the goal is to make these things go fast. You want to reduce the communication overhead, right? Any of the coherence messages, you'd like to reduce them if possible. Any explicit MPI messages, you'd like to minimize them or make them as short as possible, so that you spend most of your time doing computation and less of your time doing this overhead. And that's kind of, in a nutshell, that's kind of the challenge of the competition, right? That's it right there. Okay, so that's a lot. I went pretty fast. What questions do people have?
So like the competition, it requires that we have 3 different servers, but we can pick like whichever hardware we want, like CPU cores, the DRAM.
Yeah, I think the competition doesn't. Yeah, I think they do require 3 nodes this year, right? If I remember.
They require a minimum of 3 nodes.
Yeah, you
So
can have
come in
more.
with but I think it becomes harder to fit under the power budget after that.
Yeah, I didn't mention that. So each of these servers has some overhead, right? Each of them has a power supply, fans. There's more components here on the board than just the computation, right? There's a lot of support componentry. So that's all, if you think of it a different way, that's all overhead in terms of power. So while they say you have a minimum of 3 nodes, if you wanted to have 20 nodes, you're going to pay a fixed overhead cost and power for each of those servers. So it becomes less and less efficient from that standpoint. Possibly. I mean, I suppose you could, there's nothing in the rules that says you have to have, each server has to have its own power supply. I suppose you could come up with some system that wasn't the case. But you also have to use, I think, commercially available hardware. So you couldn't like go off design something that other people can't use or get access to. So that's a good point. Yeah, so you have to have a minimum of 3 nodes. Oh, by the way, sometimes we call a server a node. So this picture I'm showing here has 3 nodes. Each node consists of 2 processors. And then if we're talking about the AMD system, they actually have finer grains of what to call them, clusters, smaller clusters of computation. And there's different costs associated with communicating within those clusters or outside of those clusters. It's all kind of complicated. I can't remember. We have a bunch of AMD presentations from last year because each of these processors can't remember, Kai, was it 64 cores each or 128? 64, I think, right?
It's 64, yeah, and then we disable hyperthreading.
Yeah, so we disable hyperthreading, but 64 cores. So within that, there's like groups of 16 cores that communicate. If the message goes between a coherence message, if you're sharing memory between these group of 16, it's lower cost than if you go between two different groups of 16. And then if you go from this group of 64 to this other group of 64, has a different cost associated with it. And there's a bunch of scheduling tools that we use when we run jobs. So I didn't talk about that. That's a software thing. But when we run a job on these systems, you send these computational threads to different cores, and they're assigned based on the scheduler. And the scheduler has policies like, oh, try to keep them within the same group of 16, or try to keep them within the same chip, or try to keep them on the same server, right? So so I didn't draw in the picture, but there's a bunch of hierarchy there in terms of cost of computation or cost of communication, right? Which you're always trying to minimize.
I have a question regarding to the scheduler. So last 2 weeks, I tried to run something on my MacBook, and then I noticed that when I opened my job manager, it has 8 bars. I assume those are threads or cores of my M1 chip. When I try to run 3 different things, the time for each one takes much longer. When I have 2, it takes much shorter. Then I try to assign each specific CPU core to run this thing, to run one job, but it also slows down the total compute time. Does it have anything to do with the scheduler?
It could. Usually when you try to run different jobs, so in most of these machines, the last level cache is shared and the memory interface is shared. And so, for example, if you had some jobs where their cache footprint doesn't all fit in the last level cache, like maybe one of those jobs programs can use the entire last level cache. And then when you try to run 2 things at the same time, they're both competing for those resources, and they get more cache misses. Or they're waiting for DRAM because they're all trying to get to DRAM at the same time. And so that can happen. It's probably more likely there's interference between the threads than the scheduler. The scheduling overhead is very low, right? For most of these things, it's like they just they hint to the operating system, go run this thread on that core, and then not much happens after that until the thread is done. So the scheduler is involved in moving these things, initializing that thread on a particular core, but once that core is running, it doesn't really do much with it until it's done.
Then are there some ways to optimize this? So let's say I allocate this specific amount of compute usage memory for this job and do the same for the other jobs.
Possibly, kind of depends on the program. Like that would be a hint to the program, hey, you're only allowed to use this much memory. But if the program doesn't obey that hint, then it's just going to use, like you write a program that mallocs a terabyte of memory, and you tell it, hey, you're only allowed to use, half a gig of memory. If the program doesn't obey that, it's just still going to allocate terabyte of memory, right? So I think it kind of depends. But that is definitely part of this competition, is to figure out, hey, which jobs kind of are friendly with one another, right? So maybe I have a job, some benchmark that is doesn't have a very big memory footprint, right? So it can run with another job that's doing lots of memory accesses, and they'll very little interference, and those 2 run at the same time. So that is an interesting thing to know about the applications, like how memory intensive are they? How much IO do they do? What kind of resources do they need?
Yeah, interesting. Thank you.
Anything else? Okay. That was real fast. Hopefully it helped put things in context, but we can always come back and revisit it kind of, once we get down into the nitty-gritty details, go back, pop up and say, okay, what is it we're really trying to solve here? What's the fundamental bottleneck or fundamental issue to making this go fast? Okay. Andy, did you want to talk about GPUs, or Mary, did you want to talk about software in the last part, or we can call it a day?
I can talk about Expanse and getting onto it quickly. Andy, you're going to pick a different day for GPU, correct?
Yeah, I guess it makes more sense to start with, more general computing than diving into GPU computing and programming.
All right. If you guys want, we can launch into this or take a 5-minute short break, stretch your legs. So we've been meeting for a while, and I'll try and wrap up by 4, but I'll just set a timer for 5 minutes, then we'll get into, I'll put some links in the chat.
I'll be right back.
What? Yeah. Examples that'll be in my material that I'll show you. And then there's also other examples in this directory as well. CM shared examples, SDSC. And this is maintained by Marty and other people in user support. And there's all kinds of things you can do in there. So you could go find examples if you want to play with them. It's a really valuable thing. And so I'm on Expanse here in the login. And then I have the examples that are from this tutorial in my home directory. And you can also, there's a link to a GitHub repo for getting material from here. So what I'm just going to quickly go over, and I promise not to go past 4 o'clock because I uploaded this talk. It's a talk, I haven't updated it. I think I updated this material in the spring, but this one is from last year, but it doesn't change very much. The basics are the basics are the basics. And so I'll go through this very quickly. And in this Expanse 101 tutorial, the idea is it's connected to a GitHub repository. And you can cut and paste from this. So if you go and you want to try command out, you can just, try the command by cutting and pasting. So if, here's an example for looking at modules, and this is just to help you get through things faster. And it covers all the basics, like, the architecture of Expanse, which I'll skip because Brian did a lot of this, and we'll talk about other architectures, but then how to get started. A lot of you are new. And a real key aspect of working on Expanse is working with the modules. One of the things you can do is once you can log on to Expanse, you can start running parallel jobs. And so you need to figure out how to configure your environment. So I'll talk really quickly about that, managing your accounts and charging. And then it's important to be able to compile and link and then to run jobs using Slurm. And so this whole tutorial goes through everything that you need, including hello world examples to run an MPI and OpenMP, and then hybrid MPI OpenMP, and then some GPU code examples. Last time I ran them, they worked. I have a student who's in this room who's partially helping to test and debug some of this code as well that's used at part of our example Jupyter notebooks. So you can go to this online. You can, like I said, cut and paste. The idea is this is just Markdown, so it shouldn't pick up any of the crufty characters that you get when you're trying to copy from a PDF. And again, you've got a copy of the talk. I uploaded it in the chat. So you guys should all look for this PowerPoint and then the links underneath it. I think everybody but Tristan has an account on Expanse. I was just looking at that earlier. Here we go. And so Tristan, that's just because you're brand new, but Nicole says as soon as the package is sent to her, you made an account. It took overnight for me to have access to, and I could add you to my allocation. And then as soon as she gets information, she'll create your account, which means you'll have you don't have a home directory yet. But she said you should be fully capable, have everything working by tomorrow. So you can start working and getting online and logging on. All right, so I'm gonna jump into the PowerPoint. It's a little faster for the basics. So, and if you have questions, we can stop, but let me go into slide mode really quickly. Are you guys, am I backwards? Swap the displays. Is that, are you seeing my pointer and the, all right, so this is Expanse, which has got these 13 scalable compute units and then more, and it's really designed in a really neat way. Each one of the racks has CPU, GPU, and storage. Hold on, I need to shut my door. And so it allows you, it's tightly coupled. So if you can operate within the constraints of one rack, then you can get your computing job done more efficiently. And then it also has ability to use external CI. I'm not going to go through all of that. That's a picture. If you haven't had a tour, we'll be doing tours on Monday. I don't know how many of you are coming to the Data Sciences Institute. Probably not too many of you, but we can arrange a tour for the group of you next time we're all together. So you want to connect, and before that, this is a talk I give to people taking our institutes, and so we have basic skills that I think you guys already know: GitHub, Linux, workstations, and then understanding systems like that. And so you have to connect with a terminal application like the one I've got here. This is a terminal application running on Mac OS. How many of you have used a terminal application on your laptop? I would imagine CSE. If anybody I can't see all of you. If anybody hasn't, then we need to mentor that person to make sure that they can get onto the computer. So it's an external connection. I think I'll stay out. And you use the SSH, and the connection is login.expanse.sdsc.edu. And there's two ways you use your username, and those are the two ways you can log on. And so using SSH keys, we all are familiar, I hope, with SSH. If not, we have a couple of tutorials you can go look at. SSH is a way to have a stronger authentication. Everything's encrypted. You can also create key pairs and put one of the public key onto the remote machine and have passwordless login. Marty has a small talk on that maybe he could put that markdown link into the chat if he has time. But you can use something called SSH agent to set up automatic forwarding as well between all the different systems, and we have a webinar on that, and then we have some links to training on that. All right, so you're getting the idea of a HPC system is more than one device. It's a series of nodes, and the nodes have servers on them, but you don't log directly onto one of them without special permission. So you always log on to a remote access node. We call them the login nodes. And sometimes there's multiple ones on Expanse, there's two. And once you get on the node, you can request to run a job on a compute node, but you do that through a scheduler or by an interactive computing command, and I'll show you that briefly. But to get onto one of these high-end compute nodes, you need to be the one assigned to work on it. We don't want people dropping in on a node where somebody's trying to optimize performance, for example. And it also, with thousands of nodes and servers, with hundreds of servers and nodes on there, you're not the right person to be making that choice. So you work with something called a scheduler. And so this is what it looks like when you log in. You'll see a welcome to Expanse with something we call the MOTD message of the day prints out. And it looks kind of like this, and you're running commands like, what machine am I on? Who's on the machine running jobs? Let's see if I can just, who am I? I can't type on my, uh-oh. I just killed my connection. There we go. Who am I? Host name, what am I on? Where am I working? Do you guys all know Unix, so I can skip all that? If you don't, you're gonna really, yeah, I'm assuming you guys would know that. Okay, great. So I'll skip all that, but still it's complex, and like I put into the chat, these examples where SDSC maintains software and keeps them updated, they're really the place to go to make sure you've got current examples that work. And if they don't, then reach out to user support consult at sdsc.edu, where folks like Marty are there to help make sure things are working right. There's two reasons something that's in there isn't working. Either it's gotten outdated, or there's something wrong with your environment, and you need to learn to test and debug both of those, especially on a big system. So don't run jobs on the login node. You guys can use the portal. You can log into it with your username and account that runs on Expanse, and a lot of features are built into it for running things like MATLAB and R and even Jupyter notebooks. But I suspect at the end of the day, you guys will be more command line people. But if you're going to run something on Expanse and you need to run from the command line, you need to grab an interactive node so that you're not chewing up the resources on the login node. There's a lot of people logged on. A lot of people are currently logged on. And so if you're on the login node and you run a command like htop, it shows you all the processors that are available and how busy some of them are. And every once in a while you get like this guy number 7's probably running a code, and then you'll piss off a lot of people and people won't get their work done. So you want to be able to grab an interactive node. All right, so moving along, modules. Understanding the environment that you're in is pretty important. And I have a full section over here on modules. It used to be when I did my first master's thesis on the IBM SP2 at SDSC, I had to install all my libraries. And I had like 400 libraries and different programs to run an ocean model. Or what was I doing at that time? I was benchmarking Java. But I got carpal tunnel syndrome, and I had to learn to use the mouse with my left hand. I was just like all day long compiling. And then a library changes and you have to update those libraries. But there's people that do that on these HPC systems. And what people realized was, if they build an environment for you for a particular application, from the application down to what compiler that application needs, and whether you want to work with Intel or another compiler, build that environment and customize it to your application. You may have a project with 2 applications and they both need different libraries, and they conflict with each other and they're not that compatible. And so you build a module, you use the modules command to build those customized environments. It takes a little bit of work and patience, but if you can't find something, again, contact support and they'll tell you, oh, you need to use these modules. And so things can change depending on what you're trying to work. So these are your most common commands. Again, they're in here, and you can go on and you can do module list, right? And then that tells me what I'm currently working with. I'm trying to get an example for a netcdf file working, and I'm actually having to work with Mahidar because if you do module spider, that's a cool command for finding spider. Sorry, I have a broken keyboard, so I'm trying to get it repaired, but that's going to take giving up my laptop. Module spider, let's see, netcdf. And it's like, which one of these do I use? And it's not always clear if you pick something complicated. And so once you do get the formula, though, what we recommend is that you keep track of that formula and just keep reusing it. Like I have 4 module formulas listed for all of my examples that are in the system. And I'll show you a bit more of that. And so this just goes through a few examples for looking at the modules and figuring out which ones are you currently using. There's a spider will allow you to find things about, for example, what MPI options do I have? I type it here. There's a few. Do I want Intel? Do I want to use GNU compiler? What compiler? So do I want OpenMPI, and which version? Again, you can customize your environment to the versions of the software. And for the student cluster competition, this might be a valuable thing. I don't know if you guys ended up using it last year, Kai, and I don't really know, Marty, how hard it is to get it going. But if we could use it, it might make your lives easier as you're testing and debugging and optimizing your applications. I would defer to Marty's expertise on that. It may be that one year we used SPAC for building up an environment as well. There's different ways to configure how you're going to install, launch, and run an application. But unlike most people, you're going to have to install and manage the applications on that 3-node cluster. And so that's a conversation to start having with the mentors and the team once we get the hardware, or even beforehand. How do we manage them? Anyway, so modules are really great to use. Let's go back over to this. And like I said, I've written the tutorial so you can go back in and you can check your environment. It's pretty straightforward. Does this command work? Do I have the queuing system loaded in? Yes, I do. So I can use SQ. If I were to do a module reset, maybe. Do I still have SQ? Yeah, but if I do something like module purge, I'm going to regret this. Then it won't find SQ. No SQ because I didn't load it. So now I'll try to module load, what do I load? Slurm. Now it finds it. So I got rid of it. Of course, the rest of my environment is probably not going to work very well because I don't even have a compiler. But you can see with modules, you can clear everything out and then make a customized environment for what you're trying to do. I'll probably have to add some more things in here, but I'm not going to worry about it right now. All right, so that's what this section takes you through to remind you. And again, there's also, these notes are pulled strongly from the Expanse user guide, and it's always the best source to go to. I just have a bunch of examples, but the Expanse user guide will always have the most recent, relevant, updated examples. And so if you go to Expanse here and go to the user guide, then that will give you the most current information. So I try to have my examples be real world examples of what's in that user guide. So you get certain modules that are loaded in at login, and then there are some ways to troubleshoot. Like you can imagine if you're loading and unloading, you end up maybe with an environment that's not clean, and so you can just clean everything up and start again. And that's why you want to have little mini files that you have your formula in. Like here for compiling and running, we have instructions for the modules that you want to load in, and checking for what you're using, and batch scripts. So I'll get to that in a moment. Any questions at this point? How many people have worked with modules before? Just a couple of you. So, all right. Okay. So, great. So job charging, I won't worry too much about that, but you guys need to be in an account and have an allocation. So for example, you might be able to log on, but you can't do anything because you're not on an allocation yet. And so the command that you want to run is Expanse client user, and that will tell me what. Oh, so I have to module load SDSC's module, and then this one should work. There we go, live demo, and it worked, yay. So this one tells me that I'm allowed to use these projects and charge to them, and in a lot of your scripts and stuff, you'll have to charge. On your local, when we build out the student cluster, you won't have to do that. Let me see. Module examples, account management.
Oh, Mary, I have a question about the Jupyter Notebook, because in the user guide it talked about something to do the Conda environment and then launch your Jupyter Notebook. But last quarter, I try to use Expanse for my class project, and then I use Galileo to launch the Jupyter Notebook. Is that the correct way or no?
That's the correct way.
Okay.
Marty is here. Marty and I and another guy named Scott took a look at Jupyter notebooks and running them in Jupyter Hub and other applications that run on the login node. And Scott said, nope, not going to do that. It needs to be remote. So there's an architecture that's based on launching a script like Galileo. Marty has really done a lot of work to make this run properly so that it, for you, grabs an interactive node. It submits a job to the batch queue and grabs an interactive node and then returns back a link to a secure HTTPS Jupyter Notebook server. So we can probably see if Marty can take you through this guide maybe next week. I wasn't going to go over that today, but it's the way to do it. It's secure launches. Most Jupyter notebooks don't launch with a secure web server. It's HTTP because it started out with an ecosystem where you run an Anaconda on your laptop. So good question on that. So Marty, do you think maybe next week? I know we've got the Data Sciences Institute next week, so everybody's pretty busy, but maybe the week after that, we could do it.
Marty had to drop off, so.
Okay. I will ask him. It's not very long, but this is how you would run notebooks. Andy, you were going to say?
No, I just was telling that Marty had to drop off, so you can't
Okay.
ask him whether he has time next week or not. So, but I guess he's pretty busy probably with the Summer Institute, like we all will be. But at least I am not teaching on Tuesday, so I'm teaching Monday and Thursday. So if we decide to meet, I could drop in.
So yeah, if we meet on Tuesday, we decided to meet somewhere between 2 and 6 p.m. and I'm thinking 4 p.m. is a good time.
4 p.m. Okay.
Does that work for you, Andy? And you could do the GPU stuff? I know you put some notes.
Yeah. I know. I put some notes. I don't know how much time. I mean, it's hard to say because I'm very, very busy right now, in particular because Sunday next week I have to give a presentation at a conference that I still need to prepare, and I have a paper revision that's also due.
Yeah. All right, let's not worry about that right now. The Jupyter Notebook, Zhijan, there are videos you guys can look at and then ask questions next Tuesday. So we could make it a topic for next Tuesday. And I'll set up the meeting. So we'll look at Jupyter Notebooks. And if Marty can join us, he can answer your questions. And so one of the things you guys should maybe get in the habit of is going back to and I'll put it in the chat, the training catalog. This has links to our most recent, or really pretty much all of our material. And if you go back to Run Jupyter Notebooks, that's Peter Rose's, it's a different perspective. If you go back to like our Simul Institute, we didn't record things last year. But if you go back to this year, and last year we did, if you go back to the HPC and Data Sciences Summer Institute, I'll put both of these into the chat because they have built into them like 24 classes between the two of them, recordings of different topics. And so if you look at the interactive videos for Simul, there's accounts, login, running jobs, which I'm doing, running notebooks on Expanse, which Marty did. So that would take you right there. So what I should do is just put this link in here. And then CPU computing, Andy's GPU computing. So maybe if everybody could review that, then we could just ask him questions if he has time to drop in. We had the same thing for the DSI. The DSI is right here, so I'm going to put these two in here. And so these last two are, some of them overlap and some of them don't. But there's interactive computing. So we broke it up. This talk I'm going through really quickly into a lot of smaller modules. So this one isn't reflecting a new approach we have to our training, but the next version will. Answer your question, Jijan? Good question. Okay, so compiling and linking, I'm assuming you're computer science majors, so you know that there's different compilers in the world, and so this is just a section that goes over and shows you what the commands are to remind you. One thing I'll point out is you might think that the AMD optimizing compiler, which is running on an AMD device, might be the best one, but it's the compiler that's best for your application depends on the application and the system it's running on. And in some cases, GNU compilers outperform these, and they're free. These very expensive compilers that can cost $100,000 a year for, you know, multiple nodes. So don't assume that any one of these ones is the right one. Sometimes you have to experiment with them. So I'm not going to go through too much. I'll just show you the pattern for each one of these compilers. Let's go to one like I know that you're familiar with, like the GNU compiler. Clear out your modules and load these two modules, and that gives you everything you need to compile a code in using GNU. There's Fortran and C and C++, and there would be, you know, Python as well runs on these systems. And I think parallel Python works for the most part. So the compilers, like I said, my example shows you what the command should look like, and they're not all the same. And now you want to be able to run a job. So Brian talked about parallel models, so I can skip through that. Let's just go to the ways you might run a job. Like I said, getting onto those nodes is very precious. So you either run a job using a batch queue, or you want to do it real-time interactively. In the batch job, there is a service that's running that knows how to manage hundreds of nodes. I think there's 700 or 800 now on Expanse. And so, and each one of those are multi-CPU, and the CPUs are multi-core. And they split jobs up even down to how many cores you're going to use on a particular CPU. And so you couldn't figure that out. And so the batch queue scheduling system, we use one called Slurm. There's other ones, but it's pretty popular. And yes, it was named after the drink in Futurama. So you know where it came. And it does taste that bad as well. They used to give it away at supercomputing. I used to have a can of it, but it exploded, or it started leaking. It got to be old. Anyway, the Slurm job scheduler, I won't go into it too much, but it's really amazing what it does do. So you use a particular syntax in a script that is actually a Unix script that you submit to the scheduler. It looks at it, it first of all parses it to make sure it's correct, and if not, it erps back an error. And then it takes that job and goes, yeah, it's all syntactically correct, and it puts the job into a variety of queues, and these queues then run with different job priorities. So I think a lot of these terminologies should, a queue is a queue is a queue. You guys know about queues if you're computer science majors. So the batch jobs then are, what you do is you run it, you send it off, and you wait to find out when it's done. You can monitor things like SQ tells you the jobs that are running. Some are running on the shared. There's a lot. Some are running, some are pending. And if you guys know about the pipe command, I don't want to see things running, so I block them. And P is pending. So, and then you get a little bit of information, and a lot of this is available to you because you have an account, but it's not public information. Okay, so that's being able to see what's running, and once you submit a job, you wait till it starts. And if you want to know exactly when it starts, you need to put print debug statements inside your code. Okay, so if you want to run interactively, like get your hands onto a particular CPU or GPU node, I'll try this and see if it works, but it won't till I fix that. Right now, if I go to here, I'm on the login 101. Now, this one I know I have to fix this, so I'm going to let it error. I have to give it a valid account number. And so partition debug. Debug's always the fastest. You can only run a job for 30 minutes. So I mentioned you guys are all going to be on SDS173. Hit return. I got one. Now notice, how can I tell I'm on it? It says right here, I'm on that node. Who's on that node? Just me. Nobody else is on here, right? And there better not be anybody else on my machine. The only things running are the code, the software needed to run that machine. So I can now launch a Jupyter notebook, Shijan, using Galileo, or I could have gotten that notebook running through the batch queue. It depends on what you're trying to do. This is where you would compile and debug really big applications, for example. And when I'm done, I'll nicely leave it. So we call that one form of interactive computing. Running a notebook, even if you've requested it through the queuing system, is also interactive computing. And command line jobs, right? Things we run from the command. And they're not meant for compilation, but you can do a little bit of compiling, but don't run your job. If you try to run a parallel job, it should ERP and die on you. The Slurm Resource Manager, that's that representation of a cluster. And then this is just from the Slurm Quick Start Guide. This is great to learn about it. It's a server, and these are the commands. Like I ran SQ and S control. There's different commands. There's S batch is how you submit it, and this diagram doesn't contain it. But this does a lot for you and makes a big difference in your life. So partitions, what they do is they take all the nodes and they have these partitions, like is it a GPU or is it a CPU? Do I mind sharing my core? Let's say I'm running a code that I'm profiling and I do not want to share any cycles. Then I ask for one node with all 128, one CPU and 128 cores, and I run my job on there. Maybe I'm doing a scaling study. But let's say I don't really care. So I say, well, I just need 16 cores out of the 128. Then I get that allocated. That would be shared. And they're cheaper to use. You only have so many hours allocated to you. So eventually you might run out. So anyway, you pick like there's the GPU debug and there is the a CPU debug as well. And then the different states that you could be in and the common commands. This submits a job and then you can see your job, or you could see all the jobs. Usually you just want to know, is it done? And you do that by either looking at the queue, or if you have an output file, you're looking for that file showing up on you're in the directory that you submitted the job from. So the batch script, I've mentioned that this is what you write, and the syntax used by SDSC people is .sb is slurm batch. And you can use whatever extension you want. Like some people use BAT. It just, for you, how you want to name things is up to you. Slurm doesn't care. What it cares about is what's your shell, and then this magic prefix called #s batch. When it sees that line at the beginning of a line, it says, okay, I need to interpret anything with S batch. Aside from that, you can put anything else in there that you want. And the example here is just printing out your environment. I don't know if you know what the environment is, but if I type env, out ERPs a whole lot of information about my user environment. What are my paths? Who am I? Where am I? Lots of information you may never want to see again. But it's all part of your environment. And so I just give this a job name, environment, env info. I tell it the output file name I want, which is env info %J %N. And one of these is the job ID, and the other one is the name that I put up here. You can't dynamically name the job, but you can dynamically name a whole lot of other things inside this script. And so that's just my output for simple hello or env. And then you need to tell it what partition. This one's showing compute, but the fastest way is debug. How many nodes I need, how many tasks per node, and I want all the information, and what's my account I'm going to charge to, and how long I think it's going to take. If you tell the system it's going to be 1 minute, it's going to go pretty quickly because the scheduler can do something called backfilling. If it's going to take 10 hours, you might have to wait a little while. That said, the debug queue is so busy, it can take 10 minutes to run a 1 minute job. But you need these minimal, there are many more SBatch environment variables that you can set, and you can set a lot of other environment variables, just like a regular Unix. I'm assuming you guys have good Unix shell scripting experience, and if not, you'll be developing quite a bit. So then setting up that environment, in all of our examples that I write and Mahidar writes, we try to show you how to set that environment. And a novice user assumes when I launch a batch script, it inherits the environment that you're currently in. It is not true. There's so many layers of systems that your request goes through that whatever you want to be in the environment at the moment in time you run your job, you need to explicitly, we suggest you explicitly set that up in this batch script, the shell script, because you want to make sure if there's something you want, like the number of threads or a lot of information, you set it in this script. So here I purge the modules, and then I load in exactly the ones I want. And these will just load the most recent versions. And again, you can see in some of the other examples, you might need to get more specific. And then I'm just going to echo some information like environment. These are kind of precursor to Hello World. If you log on and nothing you've been doing, all of a sudden one day nothing's working, right? And this happens to all of us. Then go back to this guy and say, does this work? If it works, then you know everything up to the point at whatever work you're trying to do is good. Sometimes this simple a batch script won't work. That's when you know there's a problem with the system. It's not you, and you just email a note or look for a message that says the system's down. In that case, usually you can't log on, but having a couple of go-tos that always should work, that you never change, is really essential, so that you know when you're having a problem. Jijan, did you have a question, or are you just moving your arm?
No, I do not have a question.
All right. Anyway, and so when you've run it and you submitted it to the batch script queue and it ran, you're going to get an output file named what you want, and it's got information in it. Of course, that environment, I snipped it all out. So this is a good debugging code to have, and you can cut and paste most of this and it should work. So we'll do, I know we're getting close to 4. So here's an example, a template of MPI code in Fortran or C, but you're going to be running something in parallel. So you're going to be using message passing interface commands where this initializes. If you're initializing an interconnection of 1,000 cores, that's going to take a long time. If you're just doing 10 cores, that might not take so long. So MPI init, though, does all the pre-work needed to set those cores up so they know how to talk to each other. That shared memory, distributed memory, all those models, they all get set up. And then the comp size will tell you how many cores were asked for: 5, 8, 16, 4,000. And then what this snippet of code gets launched onto every core that you've asked for from Slurm. Same code. And then down inside the code, you would differentiate what a block of code might do if it's on a particular core. But so you ask the server, what number am I in? It's now a virtual world. Imagine virtual houses on a street. There are 100 houses. Each one of them has a house address. And it's just virtual, though, because even though you might be number 8 out of 10, the 2 actual physical devices might be 10 feet apart in the computer room. Slurm makes all that decision for you. And then you print out some information, and when you're done, it shuts everything down. And again, the finalize can sometimes take 2 or 3 minutes if you're saving a lot of data. And if you're printing out and doing a lot of debug, finalize will get everything and send everything that you want to the standard output that you've asked for. And in my batch script, I asked for everything to go export all, and I didn't say put, like you can define output for error and output for good to go to 2 different files. Mine just says everything to 1 output file. And so finalize will grab all that information, and then when you're done, you need to have your code be compiled. And in the compiler, we also suggest you have a place with, like when I'm compiling, I cap this README, I copy this, like I can go over here to the terminal, and I don't know where I am, but I'm just going to set up a new module environment, and something went wrong, so some things got loaded. These are probably old commands, and I myself need to update them. So module spider, so you can see from here I could just cut and paste and put it in there. Then I could compile, and then I submit my job, or run it using an interactive node. I check my environment to make sure it's working, and then I submit the job. I've got the batch script example here, and then to submit it, I use the command sbatch and the name of my file. It should be in here. And then there's the output file. Oh, is this an interactive one? Anyway, there's your batch script that got generated. There's something not right here. This looks like the interactive example. Oh, that's just doing a listing and looking for that output file. But there should be a line in here that shows you how to use sbatch to submit it. So I need to check that. But you get the idea of the pattern. And all of these examples run the same way for compiling for CPU, GPU, and OpenMP. OpenMP is something we don't have time to talk about today, but we'll do a session on MPI and OpenMP. Let me make a note here, though, to check. It looks like there's something that didn't get repeated. That isn't properly represented. OpenMP is a pthreads. It's thread-based computing, and so you can combine OpenMP with MPI, and you might have MPI to distribute your job across a bunch of nodes, and then OpenMP then to get more parallelization by breaking up the local work with threads. And there's a gotcha, though, on the number of threads. You can really run almost 24,000 threads on one core. But can you imagine what's happening to the OS and the CPU utilization? So the rule of thumb is if you're doing parallel computing and high-end computing, there's a maximum number of threads per core that you want to ask for to get full efficiency. Usually it's like 2 or 4. The vendor might say you could do 8, but you are going to lose some efficiency because those 8 threads on that one core are contending for the attention of the CPU and all that data that needs to move in and out. So you have to be careful and make sure you really understand a hybrid MPI. MPI distributes it to different nodes, and you want to get your data across those nodes. And then the OpenMP, which can give you, well, you ask for 128 cores, the job gets divided there, and then you can get a little more acceleration maybe with OpenMP, or you could use OpenMP, I think, to distribute it across the cores. But you have to tell the compiler and the operating system that that's what you want. If you want 1 thread per core, you have to tell it, do not oversubscribe. There's all these little gotchas about OpenMP. But later on in our training agenda, we have MPI and OpenMP on the list. We just have to figure out who has time to give it when. So that's kind of the end of this tutorial. And if we look at the training schedule, we'll figure out what we're going to cover next week, starting on Tuesday. I won't be around. It's my birthday, so I'll be out celebrating my birthday. And but again, we'll see what these topics need to be and who's available to actually present them.
Thanks, Mary. I got to run.
Yeah.
Okay.
Thank you, Brian. That
Bye.
overview was great. I learned a lot from you.
Oh, thanks.
Yeah, yeah. Okay. All right.
Happy
Well, you
birthday.
guys, huh?
Happy birthday.
Thank you. Thank you. I'll be camping out at Mission Beach, having a good time. So let's see what we can get. I know we have a request for Jupyter Notebooks. And Paco and Kai, one thing we can do is, you need to make sure that these guys could get onto the Raspberry Pi cluster. I don't know if it's available on the network, but they could go in the lab and learn some basic stuff there. While we're all still here, I'll take a few more minutes. Eventually, we have to figure out who's interested in the different applications. I know, Zhijan, it's obvious you're interested in MLPerf. You've already been working like crazy on it. I know Kai is interested in the reproducibility application. I forget what it is. What is it? Remind me. Can't hear you. Can't hear you.
My bad.
You're on. There you go.
I believe it has something. It's some optimization with Cholesky decomposition. It's been a while since I looked at the paper because I've been reviewing all the prerequisite stuff for it.
Okay. It was the reproducibility.
Yeah.
Oh, I remember now.
The block
Symmetric
distribution.
Block cyclic distribution. And I think Bob is a co-author on either that paper or the three-dimensional magnetohydrodynamic, which I believe, I forget which one, but so you guys should be looking at what's there. What we try to do in our training is make sure everybody knows something about everything, because when you get interviewed, they will ask you, Tristan, what do you know about MLPerf? So we talk about it, we have meetings. When we get into the main training, like when we get to the beginning in October, we have like 5 weeks, 6 weeks. You guys will be presenting every week, which is a good experience, but also nothing like a homework assignment that's due on Friday to make you get stuff done Thursday night. So it does help, and it helps you get organized. So take a look at these applications, and then Tristan, you're an alternate, and we have funding to send alternates, so you'll be coming along. And we've already had one person who had to move out, so Gloria is now a competition. She's moved up from being an alternate, and we'll be looking. We have 2 alternates right now, and so we need to maybe get a third person or start identifying somebody else. You never know, because life happens. And so Tristan and Jeremy couldn't make it today, but the 2 of you will be for sure traveling to supercomputing. And last year, the 2 students who, Kai was one of them, and Rachel, she's a volunteer this year, but Kyle and Rachel just made sure that things went well and helped get food. And on the way to supercomputing, they helped with setting up and learning about applications. And when we arrived on Saturday, you're allowed to do everything and work and get things running. And then Monday at 9 a.m., if we're not among the core 6, then we're not allowed to do anything more. But definitely helps to be there as a friend and support them and bring them swag. And so it's great fun. It's great fun. But at the moment, I need people to start thinking about expressing an interest and taking a look at these applications and trying to get on Expanse and scrape your knuckles a little bit. Try and do stuff with my tutorial. If you find something broken or it doesn't make sense, please send me an email or something in the Discord channel so I can fix it. I made this a couple years back. It has a feeling that it needs to be updated. And so you guys will also help me debug this. And in my opinion, what I am missing here is I'm missing a couple of things, and now my brain is tired and I'm not focusing on that. But definitely we have Galileo here, and Paco's job is to debug all of our are you still here, Fernando? Paco, is he here?
He
I can't
left.
see because I'm sharing. There, I see Andy. Austin is here. No, I think Fernando had to take off. But his job as a summer intern is helping me clean up and debug the existing test Jupyter notebooks that we have in our training repository. And those aren't connected to the Galileo tutorial, but Marty keeps this updated, and it's just magic. It's really wonderful how it works.
Mary, I have several questions. So
sure.
For the first thing is, are we allowed when we're submitting job, are we allowed to choose what type of processor or GPU to run our job?
There's only one CPU and GPU on Expanse, so you don't need to choose them. They're automatic.
I see. Because I have access to Nautilus, a research data center, something like that. And then are they also running jobs on Expanse, or are they separate?
Those are coupled in the sense that the Nautilus is the national research platform. It's evolving. They got more funding. That's the distributed system, right? A lot of people might not know what Nautilus is, but if you look at the NRP, where is it? It's too hard to find things. I think NRP should be here. No. I don't know where it is. That's not right.
I don't think there is a documentation on the SDSC website. There's some sort of like
there we go. National Research Platform. So if you go, thanks Sandy for triggering me. Let me put this in here. Nautilus is a distributed computing system with volunteer people contributing resources. And if I find the diagram, there's the systems located around the US. The school, usually the community, usually a university, community college, they get some hardware. They purchase the hardware needed to interconnect, and it's with a software and system that runs on that they put in front of their cluster. Then they can contribute. So Nautilus has SDSC as one of its many nodes, and it's a heterogeneous computing system in terms of the networking speed and the hardware. It has FPGAs, it's got GPUs, CPUs, both, all of the above, and others as well. There's a minimum requirement for the network, but I believe there's different speeds. Kai works on it as an intern, so he really should be answering these questions. So on Nautilus, and you guys are all welcome to try and use it. On Nautilus, you can request different platforms, and that's what's behind Jijan's question. But SDSC through Expanse would only be contributing Milan CPUs and NVIDIA GPUs. I don't think there's any other hardware on Expanse from the CPU and accelerator hardware at the moment.
There's a range of different GPUs available through Nautilus, so
there are.
Issue is it works very differently. I mean, you have to use containers and Kubernetes.
Kubernetes containers, correct.
Yeah, so that's very different. And it's interesting to learn, but would be one additional thing that you absolutely don't need for the super.
For the competition. Now, what we can promise is we're refactoring our HPC user training next year. We took this year off because everybody was exhausted, and we had so many changes. But what will be part of that will probably be some training on the National Research Platform. I'm being brought into some training. They do some training, but not from our perspective. So we can guarantee that for the club, we can do some NRP training. Absolutely. But as Andy pointed out, this working on Expanse is what we all need to focus on, especially for CPU and hopefully GPU. I did get my email sent off to NVIDIA. I keep calling him Andrew, but it's not. So I did send him Anthony Kaninsky and Patrick, and then I'll send a note off to Patrick when we're all done. So good question. There's so much for you guys to learn. And hope that this was interesting. Do you have any other questions, Zhijian?
Today in the morning, I was looking around the benchmark, the ML perf, and I found that there's a paper published by, I'm not sure published by whom, but it directs to a archive paper that is 15 pages, talked about everything about ML benchmark.
Oh, can you share that paper with us?
Yeah, I also posted.
Okay, yeah, what we should be starting is we usually have a Google Drive folder for you guys, a shared folder, and I make a folder for each of the applications and we upload papers there. But you could just share the link for the X archive, but I'd love to see that paper.
Yeah, let me post it into the chat. Yeah, it's in the chat.
Oh my God, it's everybody and their uncle. In case you guys, this is a big system paper. Sometimes that happens. I don't think I know any of those people because I'm not a machine learning expert, but some of our machine learning people might know them. Also, when you have somebody putting together a standard, that's a lot of work. So people might want to contribute, but they just don't have time. So yeah, that's a lot of people. Oh, this is great, Zhijian. Love it.
On top of that, I did some brief looking, and I found a paper where they did at least the training portion for MLPerf on AMD Instincts. So we might be able to use AMD Instincts.
You found a paper on that?
Yeah, I need to get the actual paper, but I've skimmed over their abstract.
Can you put that link into the chat? Oh, I can download the paper and share it with you guys. That's awesome. Semantic aware losses. What year is this?
Let's see.
2021.
So it's just, and these are two people from AMD. Perfect. This, Kai, yay. This is great. So let me see if I can download that paper. Well, usually if you just put San Diego in here. There we go. You guys are probably able to do this. Do you know that?
I think we have to use school's VPN in order to download this.
Ah, okay.
Yeah,
I'm
if you
not on
connect to the
VPN.
VPN, it should automatically work, so you don't have to, log in with a password for each journal.
It's making me sign on to business systems, and I have a corruption in my password on that. So is somebody on the VPN? Can they download that paper?
Yeah, I can do that on campus right now.
Oh, all right, Zhijian, would you do that and then just put it up into the chat?
Sure.
And
Yes.
I don't know if I started a drive for the project. I think I can stop sharing. Shared drive and student cluster competition.
Will we be able to get something like MI 300X for the AMD GPU?
I don't think those are available at all.
I don't, they announced this in May, and I think the issue with us, even if we got them, is their power draw on top of they only come in the CXM form factor. I don't think they come as cards. But I might be
I want
wrong on
y'all
that.
to try and get into that shared Google Drive, and then I'll make well, we've got already a couple of applications in there. So a new folder for ML perf. I think I prefer to put all of the applications together.
How exactly do we run the benchmark? Do we need to go to a GitHub repository and then provide the code?
For ML perf?
Sure, yeah, for
I
everybody.
have no idea. I would imagine for any of the applications, though, that you need to go to a GitHub repository, log on to Expanse, and from the go to the GitHub repository, copy the clone command, and on Expanse in your home directory or some project directory, clone the repository. Usually, you want to run it on Expanse, not externally. That's a fundamental thing that you have to do. Hold on. So can you guys all get in there? What I'm going to do right now is move everything into the apps folder. Everybody should be able to see everything under SCC23-team on the shared drive. All right, a bunch of us are trying to do things. Okay, great. So let's get some papers up in these. How many other apps do we have? We need a new folder for I was just looking at the website. All right, so we'll make a folder for benchmarks, general folder for benchmark. I renamed that file, Jijan, with the title.
Mhm.
Okay, all right, so we've got the beginning of the folders. Let me share for just a second, and then we can call it a day, or I will. Y'all don't have to stop.
Should I stop the recording right now?
Yeah, I would stop. You can stop
Sure.
it.